So our lesson today is based on integration by parts. This is for those equations that there is most definitely a product rule of some type involved. There's a formula that we're going to follow, breaking things into u's and v's. Series of steps. We're going to let one function be the u. We're going to let the other function plus the dx at the back be the dv. One of these we're going to take the derivative of, the other the antiderivative of. These are going to flow into the formula. We'll have one integration to do, hopefully, and then we'll be done. Some of the equations, though, like example 2, we will have to repeat a step. The trick is figuring out which one you want to be the u. Typically, your u wants to be, if you've got something with a power, that's your u most often, because you want your u's power to break down by steps as you go through various derivatives. So for my first example here, I'm going to try and color code it in such a way that it'll help make things a little bit easier to follow. All right. Example 1. The integral of x multiplied by sine x dx. We're going to let u equal x, or x to the power of 1. We're going to rearrange that 1 by taking the derivative. We're going to let dv equal sine x dx. We're going to divide the dx over to the other side so it looks like a proper derivative, and then we're going to take the antiderivative of it. We're then going to move to our formula. So when we plug these things in, the x goes into the u positions. So in this case here, the x is going to be at the front, multiplied by the v, which is a negative cos x. Subtract the integral of v, a negative cos x, multiplied by du, the dx. Once again, it appears I've made an error there in the first line. That should be minus the integral of a negative, I just fixed it, negative cos x dx. We simplify this a little bit. We see that we've got an integral of cos x to take, and that's fairly straightforward. Make sure you add on your plus c. Example 2. The integral of x squared times e to the x dx. Our u is going to equal the function with a power. Du then is equal to 2x dx. Our dv is going to equal the rest of everything in that integration. Taking the antiderivative gives us v is equal to e to the x. We plug it into our formula. U times v minus the integral of v du. And this time we see that we have two functions still inside the integral. So what we're going to have to do then is go back and redo this with the piece that I've underlined in blue. We're going to let u equal x, do the derivative, du is equal to dx. For the other one, it's going to look exactly the same as the previous piece in this case. Again, we're going to go into our formula, but notice that this time I'm showing that the formula is entirely contained in these blue brackets. U times v minus the integral of v du. I follow through with that. The 2 will need to be multiplied in my final step. And when I do, please remember that a constant c, if I multiply it by another constant like 2, it's still just a constant, so we can just leave it as a c, pretending that it's a different constant. For my third example, we're going to take the integral of ln dx, which previously we had thought was impossible. We're going to rewrite this in such a fashion that one of our functions is going to be 1. If you ever have a ln x, it must be the u. We go ahead and follow through with this. We're able to calculate that v is equal to x and du is equal to 1 over x dx. We go to our formula, u times v minus the integral of v du, and something nice happens in this case. Our two x's cancel over there. So I'm able to take the antiderivative And for the first time, we can see what the antiderivative of ln x does look like. I've got some problems for you to try. Hopefully this will somewhat make sense. Don't forget to read a little bit of the chapter ahead, and we'll go from there. Have fun.